Welcome back. In the previous lecture, we have discussed on phase velocity and group velocity. Phase velocity is the velocity with which a wave of constant phase propagates in a direction. On the other hand, whenever a group of waves is formed, a wave packet is formed by a large number of waves of slightly different frequency or wavelength, then the maximum amplitude of that wave or group of waves or the wave packet propagates with a velocity called group velocity. Therefore, whenever we are talking about a single wave, we are saying its phase velocity. Whenever we are talking about a group of waves and their velocity will be considered as the group velocity of the wave packet. In this lecture, we will explore more about the phase velocity and group velocity. First, we will try to find out a relation between phase velocity and group velocity. We have observed that phase velocity is just the ratio of angular frequency with propagation constant k. That is Vp equals to omega by k. From that, we can write omega equals to k Vp. Now, group velocity is represented by Vg, which is d omega dk. That is, instead of omega, we can write k Vp. So, Vg equals to rate of change of k Vp with k. So, if we differentiate it, it will be Vp plus k dVp dk. So, this is the relation between the group velocity and phase velocity. So, this equals to your group velocity, Vg. But as in the previous lecture, we have said that it is very hard to perceive this angular frequency or uh, propagation constant k. Rather, in the practical cases, most of the time we encounter with wavelength. So, if it is possible that we have a relation between group velocity and phase velocity in terms of wavelength, that will be very useful for us. Now, the propagation constant is related with wavelength as k equals to 2 pi by lambda. Now, we observe here that in the expression of relation between Vg and Vp, Vg equals to Vp k dVp dk. So, we can write it as Vp plus k d lambda dk dVp d lambda. Instead of d Vp dk, we can write it d lambda dk dVp d lambda. Now, since k is inversely proportional to wavelength, we can find out dk d lambda as minus twice pi by lambda square. Therefore, Vg can be written as Vp, then k is nothing but 2 pi by lambda. This is k. Then d lambda dk, which is minus lambda square by 2 pi, minus lambda square by 2 pi dVp d lambda. Therefore, our Vg becomes Vp minus lambda dVp d lambda. So now we have a relation between group velocity and phase velocity in terms of wavelength. So it is much more useful for us. Now, whenever, by the way, please note that in case of non-dispersive medium, group velocity is same as the phase velocity. Now, whenever we talked about de Broglie hypothesis, we have said that whenever a particle propagates, whenever a particle moves, a wave is associated with it. And we call that wave as the matter wave. Or sometimes it's called the pilot wave. Now, what is the velocity? Whether it is phase velocity or group velocity, that should be represented with this matter wave. That means, in other words, whenever we talk about the matter wave, what velocity with which the matter wave should propagate, whether it is phase velocity or group velocity. Let's try one by one. First, we check where it is phase velocity. Now we know phase velocity is the ratio of energy to momentum. That is Vp equals to E by P. Now from Einstein's relativity, we know E equal to mc square, where m is the relativistic mass. That is the mass of the particle when the particle is moving with some velocity. And momentum is the product of mass and velocity. So from that, we can write m cancelled out. So we have c square by v, which can be written as c by v by c. Why we are writing in that way? Now we know c, that is the velocity of light in free space. That can be the maximum velocity. And it is the constant. We know that value as 3 into 10 to the power 8 meter per second. And that is the maximum velocity that can be achieved. It is the maximum velocity that can be achieved in this universe. So if the particle is moving with a velocity, that velocity v, this velocity v must be less than the velocity of light in free space. That is, v must be less than c. Therefore, v by c, that v by c is smaller than 1. So v by c must be less than 1. Therefore, you are dividing c by a quantity. You are dividing c by a quantity which is less than 1. Therefore, the whole quantity c by v by c, that is c square by v, must be greater than c. And that means Vp must be greater than c, which is impossible. Which is impossible in this real world. Therefore, in simple words, the phase velocity cannot be the velocity of a matter wave. The phase velocity cannot be the velocity of that matter wave. Next, our option will be group velocity. So we'll observe that whether that group velocity is equal to particle velocity. Why? Because as we have discussed during de Broglie hypothesis, that whenever a particle propagates, particle moves, a wave is associated with it. So the wave is associated with the particle always. That means the particle velocity must be same as the velocity of that wave. The velocity of the particle must be same as the velocity of that wave. Otherwise, the wave and the particle cannot be associated with each other always. We'll try the non-relativistic case first. That means normal Newtonian mechanics, and we assume a free particle, that is, whose potential energy is zero. That means the total energy of the particle can be represented by its kinetic energy, which is p square by 2m. Now, our group velocity vg is dE dp. Therefore, this E can be written in terms of momentum as p square by 2m. So if we differentiate it, we get 2p by 2m, that is P is nothing but mv. Therefore, it is v. So, with the help of non-relativistic mechanics, we observe that group velocity is indeed equal to the velocity of that particle. Let's try it relativistic case. In relativistic case, the energy can be written in terms of momentum as E square equal to p square c square plus m naught square c to the power 4. And m naught is the rest mass of that particle. Since we require dE dB, to find group velocity, we differentiate this equation with respect to momentum, and we get this quantity. Therefore, group velocity dE dP equals to pc square by E. Again, if we use E equal to mc square, then Vg again is equal to P by M, which is V. Therefore, whether we use non-relativistic mechanics or relativistic, we observe that group velocity is equal to particle velocity. That means the group velocity is the velocity of that matter wave. It is not the phase velocity with which the matter wave associated with a particle moves. It is the group velocity. Let's try to find out the product of phase velocity and group velocity, because that product is indeed an interesting one. So if we consider phase velocity, that can be represented by the ratio of energy to momentum, that is Vp equals to E by P. E can be represented as mc square as before, and P as mv, so that Vp equals to c square by V. Now we know that group velocity is equal to particle velocity. That means we can write particle velocity equals to Vg, group velocity. So instead of V, we can write Vg. So Vp will be c square by Vg. In other words, Vp into Vg equal to c square. See, the velocity of light in free space is constant, 3 into 10 to the power 8 meter per second. Therefore, c square is a constant. Therefore, the product of phase velocity and group velocity, is a constant quantity. This quantity is a constant, and that constant is nothing but square of velocity of light in free space. Let's do a numerical. An electron has de Broglie wavelength 2 picometer, that is 2 into 10 to the power minus 12 meter. Find out the phase velocity and group velocity of its de Broglie wave. That is, we need to find out the phase velocity and group velocity of the associated matter wave of that part of that electron. Now the point is, whether you want to estimate phase velocity or group velocity, you require either omega and k or energy and momentum. But in this particular problem, neither is supplied. Rather, wavelength is given. So we have to utilize it. According to de Broglie hypothesis, we know the relation between momentum and wavelength. So we use it. Momentum can be represented as h by lambda. Wavelength is supplied. So if we put the value of Planck's constant and lambda is given in this question, we can get momentum as this. This is our momentum. What other quantity we require to find phase velocity? Say we require energy. Now, from the relativistic mechanics, we know energy can be found out from the expression of equal to root over p square c square plus m naught square c to the power 4. Where p is already been estimated with the value. C we know. M naught is the rest mass of the electron, which is we know 9.11 into 10 to the power minus 31 kg. So put the value, get the value of C, and if we estimate E, it comes out to be this amount of joule. So now both E and P are known to us. The value of energy and momentum are known. Therefore, we can easily estimate the phase velocity in terms of energy and momentum as equals to Vp equals to E by P. If we put the values, we get Vp as this meter per second. Next, we need to estimate group velocity. From the product of phase velocity and group velocity, we know that Vp into Vg equal to c square. Now Vp is already been estimated. Therefore, group velocity can be written as c square by Vp. C, velocity of light in free space, is known. Vp is already been estimated with the values, and we get the group velocity, that is the velocity of the matter wave, is 2.31 into 10 to the power 8 meter per second as per the question. And remember, this is the velocity with which the associated particle moves. That is the particle velocity also.